Okay,
And
now it's okay.
now
Yes.
it's okay. Really sorry for this.
No, that's no.
Okay, so thank you to the organizer for letting me speak. So I'm presenting something which is quite related to the last talk. If it's definitely the next step. So um, I will talk about Arborea nasutitermes. So you probably familiar with the fact that termites can build a fantastic structure, which are very impressive, and maybe also with the fact that their shape can change a lot according to the species and place where this structure appear. And the main question of our project was trying to establish a relationship between growth and form. So how growth mechanisms can lead to a certain final shape. And we all agree on the fact that nest construction must be a self-organized process. This mainly because there are a lot of individuals at work, and because the final result is something which is order of magnitude larger than the single individual worker. And of course, there is likely some stigmergy at place. So the fact that the worker is not in full control of their own work, but instead just is responding to some local stimuli. And if its action is modifying the environment, well, if the stimuli come from the environment, there can be a positive feedback loop that can explain the final complexity of the object, even if the interaction rules are quite simple. So with this in mind, we were particularly intrigued by Arborea nasutitermes that you can see here some pictures from different species. And the reason is that different from other termite nests, if you see at the bulk structure of this object, you can't really see a hierarchy. So you can't really find chimneys, corridors, and other particular architectural structure that you can see in other termite nests. So we went to the field and tried to see what this looks like. But the problem is that it's like as other termite nests, the exterior of the nest is covered with a crust, which prevents from any observation. So the only thing you can do is to breach the surface. You have seen many of these videos, I guess, and see what happens. But the only thing we can learn is that they use feces that they drop through the abdomen, and also particle of soils that they bring in mandibular, but we can't really see how the bulk of the structure grows. So for this reason, we try to use a different approach, which is looking at the final shape and infer from this the growth mechanism. And this demanded two parallel work. One side, we went to the field and collect some samples that we scan with a CT, so the same device that Kamal used, and then compare this 3D shape with the issue of a model that can possibly mimic a termite action. Of course, in order to make this comparison, we need a quantity. And I want to convince you that the quantity which is characteristic of this nest is straight away curvature. So what Daniel just described. And in particular, I want to convince you that what is common to this nest is that the wall surface often remind of a saddle. So if you want something that is nor convex nor concave, but differently curved according to the direction on which you are working on. And so just a very quick reminder to understand the following of the talk. So when you are in 1D, in order to characterize the curvature of a line, you need to draw one tangent circle, take the radius, and then the reciprocal. So the larger the radius, the smaller the curvature, and vice versa. In 2D, one circle is not enough. We need two. And with these two, we can define two principal curvature. And then playing again with these two principal curvature, we can define two characteristic quantity, which are the mean curvature, which is just the mean of the two curvature, and the Gaussian curvature, which is the product. And I want to convince you that using these two quantity, I can characterize all surfaces. For example, for a sphere, two principal curvature are the same, so same sign, so the product must be positive, while the mean is different from zero. In a cylinder, you have one direction which is flat, so curvature is zero, and the product of the two must be also zero, while the mean is not zero. And finally, the kind of structure I'm interested in, saddle shape, you have two different signs for the two different curvature, so the product must be negative, and the mean can be quite close to zero. So the final aim of this project was trying to find a place for our Arborea nasutitermes nest in this diagram, where you have vertical direction gamma, so the product of the two curvature, and horizontal direction h, so their mean. And of course, we are left with the most difficult part, which is trying to find a good model. And there are examples in the recent past research. So we have the author here in this conference that put together agent-based model with the interaction with sigmergic Q like pheromones. And of course, constrain the movement of agents to the fact that the environment is growing, so it's changing, which had very nice results. But we wanted to be even more stigmergic in a sense, because we did the hypothesis that curvature is the only guidance for our termites in construction. So as curvature is a property of the substrate, we don't really need to simulate the presence of agent. We can just simulate a substrate, which is evolving as a function of its own shape. So to do this, we use a phase field approach, which means that to model our nest, we work like in a tomography. So we have a scalar field, let's say an intensity field, which move from 0 to 1. And whenever we have high intensity, we are in the wall. And we have whenever we have low intensity, we are in the empty space, so 0 to 1. And of course, we need to define the surface of the wall, which is just the isocontour f equal 0.5. And now we need to give a law for the evolution of this field, which is the evolution of our nest. And to do this, we do the hypothesis that the growth happens where mean curvature is high. For example, at the tips of these drawings, as you can see here. So at the edges of the wall, there is growth, while whenever there is no curvature, for example, saddle shaped, you don't have grow anymore. So this is the reminder of the last talk. So if we implemented this in a simulation model, and we observed that we can have the growing of complicated 3D surface that, of course, are not identical to our nest, but very similar. And there are many reasons for this. One is that when a part of the wall have grown, they can't change, even if they could in the model, but they definitely don't, which is very similar to what we observe in nature. Another interesting feature is the fact that our wall grow and can both branch, as you can see here, but also reconnect. And this is very important to have a system which is at the same time growing, but also making some very intricate structure. And finally, something which is very interesting is that if you forbid the growing of your field in your simulation box at some part, for example, here at the top, then you see the formation of this layer, which becomes a roof, exactly like in our natural nest. So trying to be a bit more quantitative, we also observe that in both simulation on the left and nest fragments on the right, there is the appearance of a typical distance, so a typical size that is the size of the tunnels. And also the fact that according to different initial condition in our simulation, we can match different degree of isotropy. So the fact that, for example, the spacing of the tunnel doesn't look the same according to which direction you are looking to. And finally, of course, our first aim, so mapping the value of curvature in this nest. So we have here on the left mean curvature, on the right Gaussian curvature. And as I anticipated, mean curvature is mostly close to 0, so definitely similar to something which is saddle shaped. And this is confirmed by the fact that Gaussian curvature is mostly negative, again, which is a blueprint of a saddle shaped structure. So the position of our nest in this diagram is definitely lower bottom in this diagram. And being a bit more, again, quantitative, I constructed here a cumulative density diagram. So in each of these panels, you have the mean curvature at the horizontal and the Gaussian curvature at the vertical. And you see that the shape of these lines, which are just a different cumulative probability, are similar if you consider simulation and nest in the isotropic case and also in the anisotropic case. As something which is interesting is that if you consider a random surface, so here top right, so a surface which is obtained just taking a noisy scalar field and applying a filter which save just one typical wavelength, which correspond to the, if you want, to the corridor size. Well, the surface that you obtain in the end have similar curvature properties of both our simulation and real nest, which is quite interesting because we used a simulation from a model which is deterministic and extremely simple. So that's it. And thank you for listening and for our many collaborators.
Thank you very much, Giulio. This is very